All right, let's try something wild. Let's build a world. No, not a planet with mountains and oceans, but a living, breathing system where every single piece is connected. In this explainer, we're going to do just that. We're going to build an ecosystem from the ground up, piece by piece.
So, think about this for a second. A forest, a pond, and an aquarium. I mean, on the surface, they seem totally different, right? One is this massive, sprawling world of trees, another is a calm little body of water, and the third, well, it's a glass box in someone's house. So what's the common thread here? What's the one big idea that ties them all together?
And there's our answer. They're all ecosystems. It's a term that was coined by a scientist named Arthur Tansley, and it's brilliant in its simplicity. It's any place where living things, the biotic stuff, are constantly interacting with their non-living environment, the abiotic stuff, like water, dirt, and sunlight. It's this beautiful, constant dance between life and the world around it that makes an ecosystem what it is.
Okay, so if we're going to build one, we need to start with the blueprint. You got to know the basic layouts because ecosystems aren't all created equal. They fall into some really big, really distinct categories.
The first split is super obvious: land versus water. You've got your terrestrial ecosystems on one side, forests, deserts, you name it. And on the other, you've got the aquatic ones, ponds, rivers, oceans. Simple enough. But there's another way to slice this, and honestly, it's a lot more interesting. And that's the divide between natural and man-made systems. A forest just runs itself, right? It's self-sustaining, packed with biodiversity. But a crop field, that needs our constant help to keep going. And this shows a really fascinating trade-off. Our man-made systems, like farms, have super low biodiversity, but their productivity, the sheer amount of stuff they grow, is off the charts.
Okay, foundation is laid. Now we need to populate this world of ours. And in any ecosystem, every single living thing has a job to do. So let's meet the main players on the team.
The easiest way to think about it is like a city. First, you've got the producers. These are the power plants of our city, the plants and algae that take raw solar energy and turn it into food. Then you have the consumers. These are all the residents, from herbivores to carnivores, getting their energy by eating the producers. And finally, you have the unsung heroes, the decomposers, the city's cleanup crew, the bacteria and fungi that break down all the dead stuff and recycle the nutrients right back into the system. Absolutely crucial.
So we've got the place and we've got the players. But how does it all actually work? Let's pop the hood and take a look at the engine room, starting with that vital recycling process, decomposition.
You see, decomposition isn't just one thing. It's more like a 5-stage assembly line. It all kicks off with fragmentation. Think of earthworms shredding up dead leaves. Then leaching happens, where water washes some nutrients down into the soil. After that, catabolism is where the real microscopic magic happens. Bacteria and fungi chemically break it all down. This leads to humification, creating that dark, super rich stuff called humus. And finally, mineralization is the slow release of all those nutrients from the humus, making them available for plants to use all over again. The cycle is complete.
And you know, this whole process doesn't just happen at one speed. Things like sugar, warmth, and lots of oxygen really put the pedal to the metal. But tough materials like lignin and wood, or cold, low-oxygen environments, they slam on the brakes. It's exactly why a log might take decades to rot in a cold forest, while a banana peel in your compost bin disappears in weeks.
All right, next up in the engine room, how does our ecosystem grow? We measure that with a concept called productivity. It's basically just the rate at which new living matter, what scientists call biomass, is created. You have primary productivity, which is all the new stuff made by producers, and then secondary productivity, which is the new biomass created by the consumers who eat them.
Now, here is the most crucial part of this. Plants aren't just selfless little food factories. They need energy to live too. The total amount of energy they capture is called gross primary productivity, or GPP. But then they use some of that for themselves. What's left over for the rest of the ecosystem to eat? That is net primary productivity, NPP. And honestly, NPP is the number that really matters. It's the actual food on the table for everyone else.
So, how much NPP are we talking about for the entire planet in a single year? Get ready for this. It is a mind-boggling 170 billion tons of dry organic matter. That's the entire energy budget for basically all life on Earth. But where does most of it come from? Well, the answer might actually surprise you.
Take a look at this. The oceans cover more than 70% of our planet, but they only account for 55 billion tons of productivity. Land, which is just a fraction of the surface, cranks out a staggering 115 billion tons. So, why? It's simple, really. Sunlight. Sunlight is the fuel for this whole engine, and it just can't penetrate deep into the ocean. No light, no photosynthesis, and way less productivity.
This brings us to the ultimate currency of life itself: energy. You can't have an ecosystem without it. So let's trace how power actually flows through the grid of the world we're building.
So everything starts with the sun, of course. But here's the first bit of inefficiency. Less than half of all the solar radiation that hits the Earth is even the right type of light for plants to use. We call that usable slice of the pie PAR, for photosynthetically active radiation. And it gets even less efficient from there. Of all that usable light that actually reaches a plant, it only manages to capture and turn about 1 to 5% of it into chemical energy. That's it. That tiny, tiny sliver is what powers almost every living thing on this planet. It's incredible.
And the inefficiency just keeps going right up the food chain. This is where Lindemann's 10% law comes in, and it is a fundamental rule of ecology. It basically says that when an herbivore eats a plant, it only gets about 10% of that plant's energy. The other 90% just lost, mostly as heat. The same thing happens when a carnivore eats that herbivore. This is the simple reason why there are always far, far fewer predators than there are prey.
So how can we visualize this whole structure of decreasing numbers and energy? Well, ecologists came up with a pretty simple but powerful tool to do just that. It's called an ecological pyramid.
In a typical ecosystem on land, say a grassland, the pyramid of biomass looks exactly like you'd expect. It's upright. You have this huge, massive base of grass, then a smaller level of the herbivores eating it, and an even smaller level of carnivores at the very top. Makes perfect, intuitive sense.
But then, you go look at a pond or the ocean, and something really bizarre happens. The pyramid of biomass can be inverted. It can be upside down. How is that even possible? Well, the producers are these microscopic phytoplankton. They reproduce like crazy and get eaten almost as fast as they're made. So at any single snapshot in time, the total mass of the phytoplankton is actually less than the mass of the zooplankton that are eating them. It's pretty wild.
But here's the unbreakable rule. While the pyramid of biomass can get funky and invert, the pyramid of energy is always upright. No exceptions, ever. Because energy is always lost at each step. Remember that 10% law? The producers at the bottom will always have the most energy. It's a one-way street, and you're always losing power along the way.
Of course, these pyramids are fantastic models, but we have to admit, they're also a huge simplification of a much messier reality. They don't really account for complex food webs where one animal eats lots of different things. They completely leave out our essential cleanup crew, the decomposers. And what do you do with a creature like a human, an omnivore that eats at multiple levels? The simple pyramid model just kinda breaks down.
And this really gets to the heart of it all. An ecosystem isn't a neat and tidy pyramid. It's a tangled, beautifully complex web. And while our models help us understand the basic rules of the game, they can never fully capture that staggering complexity. So it leaves you wondering, if a simple pyramid isn't enough to tell the whole story, what kind of model ever could?